Thank you, Sebastian. So our next speaker is Andrew Eck, Andy. Andy is going to tell us about optimizing and parallelizing algorithms in interpreted languages, and this does have a component that you can follow along on your own laptops.
Cool. Yeah, and if people are using those interactive notebooks, if you're using the MATLAB one, I'd recommend running it directly in MATLAB using the M file. And if you're doing the Python one, I would try to run it in the online Jupyter notebooks. So yeah, so that's what I'm going to talk about today is optimizing, parallelizing code in higher level interpreted languages, specifically MATLAB and Python here. Okay. Declaration of interest and biases. So I've got no interests or biases here. Outline of what I'm going to talk about. First, we're just going to go over some definitions. Second, we're going to talk about how to find where in your code might be slow, different approaches and tools you can use for that. Third, different approaches to make things go quicker with your code. And lastly, talk about some what happens when you parallelize your code, unexpected things that might happen, reasons to do it, not to do it, and so on. So for context, my background has been mostly MATLAB in industry, and then for the last couple of years working in Dr. Wheelock's lab, applying MATLAB to brain model statistics generation kind of stuff. So most of my knowledge is in MATLAB, but also I've investigated some of the Python behaviors for like parallelization and some of the built-in functions, and there's decently similar behavior here. So I'm going to try to address both MATLAB and Python today. And in our lab, we work with pretty big data sets doing a lot of runs on models. So we're working with data with tens of thousands of functional connectivity edges, thousands of permutations, thousands of subjects, and our variables can be from 1 gigabyte to close to 100 gigabytes sometimes. So for us, sometimes there's really great value in targeted optimization for running these models when you're running certain blocks of code tens of thousands of times. So just the top level, when we talk about what interpreted and compiled languages are, interpreted is just you have a line of human readable code, and just one at a time you pass them to the computer, it turns it into code to talk to the hardware, gets a result, passes it back. That's in comparison to compiled code, where it just turns all of your code at once into machine code. So usually when we're working in MATLAB and Python, we're working in that interpreted mode. They both do support compiling your code. MATLAB, there's some overhead and some confusing parts that happen. Python is pretty straightforward. Both of them can save some time, but not nearly as much as it's not going to get you close to running in a lower level language like C or C++. So you can certainly run your code compiled, but there's more savings to be had, I would think, when you look closer at your code. So when we talk about high and low level languages, MATLAB and Python are high level languages in that they have features to make writing your code easier, but it's generally at the cost of optimization and performance. So they do a lot of memory management for you. They allow you to do dynamic typing. They have debugging stuff. So there's overhead that comes with these languages that's just important to know about that might make them a little slower, but makes your writing your code a little easier. So when we're talking about trying to optimize our code, there's a saying in software engineering that is make it work, make it right, make it fast, in that order. So the first thing you want to do with your code is just make it work. Get something together, put it together to make it work. Then you'll understand better what all the pieces of code you need are, how they have to talk to each other, and then you go profile your code, which is figuring out what parts of your code actually are the slowest running. You don't want to spend a bunch of time trying to optimize something that turns out is only 1 or 2% of your total runtime. You should focus on the stuff that is actually the biggest performance hit. So some strengths and weaknesses of MATLAB and Python: they actually run really quickly for a lot of their built-in functions and for linear algebra operations. So, and that's usually because they're just talking to compiled code from a lower level behind the scenes, like C++ or BLAS operations. What they're typically slow at is basically everything between those. or at least compared to low-level languages. So if you have loops, if you're trying to allocate and deallocate really big matrices, if you're trying to really big matrices, resize matrices, a lot of that stuff will add extra runtime to your code, affect your performance. So definitely try to avoid those. And usually that's where you would focus on optimizing your code. So how do you figure out what parts of your code are actually slowing you down? So the first one is really simple, is just basically a stopwatch-like function. So both MATLAB and Python provide functions that basically work like a stopwatch. MATLAB's got tick and tock. Python's got this time module. And just all you would do there, you find the block of code of interest, you start a timer right before you do something, do it, figure out how much time elapsed. So at the bottom left and right here, I've got examples of doing that in Python and MATLAB. These are really nice just for comparing two really small algorithms together, or for figuring out how long a particular block of code takes to run. But you should focus on really small blocks of code for this. And also it gives you a decently accurate idea of how much time really is passing, that the timer functions don't add a lot of overhead to your total time here. And that's in opposition to profilers, which kind of help you fix the solution from the other end. They, both MATLAB and Python do provide profilers for your code, which is, they're really well-written and cool tools that these languages provide that you can start a profiler, run a bunch of stuff, and it'll give you a detailed breakdown of every line that ran in between when you started and when you stopped this profiler. Organize it by, here's how many times you called this particular function, here's how much time you spent there. So really useful way to profile complicated functions. So the MATLAB, if you've got the MATLAB tool open on your computer, this is just a sample of a couple different ways of doing a particular algorithm that I did for Mariah's lab, comparing speeds of each of them. So hopefully this is supposed to be a video. Okay, well that's a bummer. Well, if that actually output, the MATLAB profiler bottom line would look like this table right here. This is basically a screen cap I got of it before. Each of these line numbers, you can actually click on them usually, and it'll let you drill down into, like, within that function, like line number 10, see in that line, maybe it called other functions and how much time did they take. So very useful tool there. That video doesn't work. Oh, no, I just needed to click it again, sorry. So here's exactly what the MATLAB profiler looks like. So I'm calling profile on, run the code, profile viewer, and then this cool interactive window comes up. So it'll show you line by line how many times it was called, percent of time of the total runtime, and at the bottom it'll show you line by line, highlight the particular lines of code that are the slowest or take the most time in your program. So highly recommend, if you're working in MATLAB, trying to optimize anything, the profiler is a really great tool. Next, so if you've determined parts of your code that you'd like to speed up, what kind of tools do we have to address that? So one of them is this idea of vectorizing your algorithms. And that's basically a term that is, you look for something that's happening in a loop, and you see if you can replace it with one single call to a built-in function or a matrix operation that uses all of your data at once. So it saves you time because it will save you the overhead of, like, loop management that both of these languages have behind the scenes, passing memory down to built-in functions, getting it back, even incrementing the loop variable can be some big fraction of your code if your loop is simple enough, and I've got an example of that later. So this idea of vectorizing comes from this idea of the space-time trade-off, which means usually if you pass more memory to something at once, it'll happen, the computation will happen faster. So you give something more space, it'll take less time, and the other way around, if you don't give as much of your data at once to something, it'll probably take more time to complete. So yeah, for vectorizing, the easiest one for sure is look for any place where you're calling a built-in function and see if that built-in function accepts all of your data at once instead of if you're calling little bits at a time or one at a time. That'll save you some time. And the second one is see if you can replace loops with a matrix operation. So you got to think back to your linear algebra classes, see if you can figure out a way to do a vector or matrix multiplication to get rid of the loop. Or, and I'll talk about this later, there's this, both MATLAB and Python have this idea called broadcasting, which is a way for, instead of looping at the top level in MATLAB and Python, it's actually just one line in there, and then the looping effectively happens in the underlying, like C++ and BLAS functions. And that's, both of the interactive code files are based on this broadcasting technique. They both have broadcasting, they both have profiling in there. So this is just an example of how much time just looping, how much overhead your looping might cause compared to just running everything at once. So this is a MATLAB example. I'm just generating a sine wave. The left one, generating inside a loop, one point at a time. The right one, create a big vector with all the points, and then create a sine wave for all the points. And the difference between them is about 70%. So 70% of the time on the left is just overhead of storing variables going through your loop. So just to demonstrate the savings you can get if you get rid of loops in your code, if it's possible. Secondly, you can try to vectorize your own functions. So a lot of this is going to be, again, using linear algebra tricks to try to make your code go a little quicker. So this is an example of you're trying to get a 2D matrix, say, where each row is 1, 1, 1, then the second row is 2, 2, 2, third row is 3, 3, 3. If you just knee-jerk reaction, how would you do this? You'd say, oh, I would just loop through the rows of my matrix, multiply the first one by 1, second one by 2. Okay, that's a great start. But on the right, you can instead maybe make a vector that has all the multiplications of each row you want, and then do a vector times matrix operation and just get it that way. Both of them give you equivalent results, but one of them is 62% faster than the other. So again, just another example of try to look in your code for loops where just frequent multiplications are happening. See if you can replace them with a matrix operation or something else. This one took me more time to understand. It's a little more complicated. This broadcasting idea, which is if you are trying to do a looped operation on two things, two variables you have, instead of looping directly in Python or MATLAB, you can do an element-wise multiplication, and depending on the shapes of each of the blocks of data, behind the scenes it will actually loop for you based on one or the other. So the bottom point here is, the two steps are just reshaping your original data to the size it'll do the looping you want, and then after that, doing an element-wise multiplication. So element-wise is just dot asterisk for MATLAB and just straight up asterisk for NumPy. The bottom point here is how it kind of works. So if you have each of the things you are multiplying, they have the same number of dimensions, but each dimension might have different numbers of elements. The number of elements in each of them either has to match, or one of them has to be 1, and the other one has to be a number greater than 1. So if the elements match, both of them will loop at the same time, effectively. If one of them was 1 and the other one is n, say, then the one that's n will loop every time, and the dimension that's 1 in your other variable, that'll stay constant. So both of the scripts I provided have a more in-depth example that I hope gives a better example of this. So yeah, this is just a 2D example. Since I think I might run a little short on time, I don't know if this one's as instructive as the notebook one, which is on the next slide. So Some background for this. We're just trying to get a covariance. This is sample code that I wrote for a project of Mariah's, where we're just trying to get covariance of some error of some model we were trying to fit to connectivity data. So just initializing some data in the second block for typical data sizes we would see in doing our brain imaging models. And then there's a block for one method, which was the first one we tried. And then after that, there's the broadcasting version of it. And in this Python example, I think there's a 90% time savings. So it'll just run through each of these blocks here. So, yep, just defining sizes of our data, just initializing the data with random stuff. So then this block right here, this run looping algo, this thing I'm highlighting here, that's the main thing we're looking at. So we're looping over FC edges, and there's a ton of FC edges. We're doing an outer product there. That's the main part of our code that's taking time here. Right, so none FC edges, I just highlighted that. We're running it 50,000 times. This is output with Python's profiler at the bottom, so it took about 1.06 seconds to run. And here's all the things that happened, ordered by how much time they took. So you see right up at the top, about half the total time was that outer product. Now this second method, the second example is the broadcasting example, and that's basically these lines I'm going to highlight right here. Yeah, and this group contribution line right below that actually is part of it too. So yeah, those three lines are basically the equivalent of that loop before. So when we run this, the previous one took what, 1.06 seconds, and this one's 0.076 seconds. So that's over 90% quicker, giving you equivalent output just by changing to reshaping your data and doing element-wise multiplication to get this broadcasting effect. And then to make sure we're not crazy, we subtract them from each other, the results of each method, make sure they're the same. So yeah, that's, if you want to run that in your own time, that's just what all the blocks of code mean in that notebook. The last main thing I'm going to talk about is parallelizing your code. Most of this is going to come from my experience with weird stuff, or at least to me, that happened in MATLAB, and as far as I can tell, also happens in Python. So mainly things to look out for and be aware of when you're trying to speed up your code and decide whether or not you should even try to parallelize. So some advantages of parallelizing your code. Oh, I'm sorry, first off, so Python, you can do this with their multi-processing package. Just download it, it's available right away, pretty easy to use. MATLAB, it's gonna cost you a little bit more money for the toolbox. It's the parallel processing toolbox. Just buy that as an add-on, then you can do parallel processing there. So some advantages of this are you can take advantage of all the available CPUs on your machine. So these days, even laptops have multiple cores. A lot of times, some of them might be idle while you're running code. So if you think they might be, then you can try to just have all of your cores running at the same time, and that'll reduce the total amount of time it takes to run. Or you could just run something in the background while you do other stuff. So that's another advantage of it. Some drawbacks when you parallelize your code are that there's overhead in starting all these parallel processes. So at least in MATLAB, you basically reserve a set number of cores and say, all right, you cores are going to be used for this operation, and here's the data you need. So each one of those cores actually starts up its own mini MATLAB compiler or MATLAB interpreter. So that takes a little bit of overhead to start that. And you have to copy the data to each individual worker on the process. So that's a memory cost, that's a processing cost. Similar things happen in Python. When you do multiprocessing, each of those threads you have to copy the data to each of those threads. The other drawback of parallelizing is that you lose this implicit parallelism bonus. So I will talk about what that means on the next slide, because this is something I didn't expect happened, but I verified it does. And that's that even if you don't explicitly tell your code to run on multiple cores of your machine, It will. So a test on our server with MATLAB, we have, I think, 256 CPUs available on our server. If you ran a big enough operation, it would automatically try to get every free core it could. And if you use a big enough matrix for one of our tests, it took 90% or 90 out of 256 of the CPUs running at 100% if you're doing a big enough operation. This is without the parallel toolbox. This just happens implicitly. I don't believe it's able to be turned off or controlled at all in MATLAB. I believe something similar happens in Python, where if you run a function, if it's big enough, a big enough linear algebra operation or built-in, it will just try to take advantage of all the cores that are available, which on its surface seems like a useful thing to happen. But if you don't know this is happening, then you might not realize that parallelizing that code will not really gain you as much. Because when you parallelize, it sort of reserves, each worker has one CPU now instead of all the CPUs on your machine. So if you run one thing non-parallel, it'll probably run a lot slower in parallel on one CPU. And I've got a benchmarking example on the next slide of that. So again, in MATLAB, here, similar example of what I talked about before, make a really big matrix, invert it once, and see how long it takes. On the left, doing it just on my own laptop. On the right, doing it in a par for loop, which is a parallel thing MATLAB does, where you just say, okay, this CPU, you alone are going to try to invert this matrix. And if you look at the comparisons and run times at the bottom, even though they're doing the exact same thing, just the one on the left is not in parallel. It's using all the CPUs just automatically. The one on the right is running on one parallel worker that only has one CPU. You can see that it's the one on the left is using multiple CPUs without really telling you. So the main reason why knowing about this is good is that if you are looking at a block of code and thinking, oh, I can make this faster by parallelizing it, maybe not, because it might, if you're only running one CPU on that block of code, maybe it'll probably run slower than running on multiple CPUs at once. So I've told you all about the reasons why parallelizing might not be great, but when is it a good idea to parallelize your code? So number one, I don't think it's as applicable here, but would be real-time operations. So if you have multiple blocks of code that need to be continuously looping and talking to each other, and they run at different rates, then yeah, parallelizing is the only way to do it. And then in non-real-time stuff, the specific situation you'd look for is you're running a loop with a lot of iterations. The number of iterations is way more than the number of workers you have. The reason why that's useful is because each worker you start has a bunch of overhead for starting the interpreter on that worker, copying the data to that worker. So your first iteration on all your workers will be pretty slow, and then it'll finally get up to speed. So to get the most out of parallelizing, you want to have way more iterations than the number of workers that you're splitting those iterations up among. Again, another point is that each of those loops should probably be decently complicated, a bunch of commands that you've written that aren't built-in commands. The reason why that's good to think about is because for these built-in functions, there might be implicit parallelism happening anyway, even if you don't parallelize your code. But if you're doing something that you built yourself that's at least 5 or 6 lines long, then yeah, it probably won't be automatically using every CPU it can, unless you explicitly parallelize it. Also, your data sets can't be huge for this unless you figure out a way to not copy the data to each parallel thread that's running. I'll talk about that in a second, but in general, it seems pretty hard to not explicitly copy your data there. And the last thing is that you need to make sure all the work that's happening in your program should be able to be split into roughly equal chunks. So each iteration should take about the same amount of time. If you have something where the first iteration is really quick and the last iteration is supposed to be really long, what ends up happening is that one of your workers runs and does the really quick stuff and then just stays idle, waiting for the other ones working on the harder stuff to finish up. So it actually just makes your code slower just automatically there. So when you're setting up your pools, so in Python, you can use this multiprocessing. There's a process module there that you can use to start processes on different threads. And in MATLAB, it's this par pool example. And at least for MATLAB, typically each of those parallel processes just reserves one CPU for itself, and anything that runs on it will only use that one CPU. And then when you start a job on your pool of workers, all of those iterations that you're running are usually divided evenly among all of the workers. And lastly, just summarizing the overhead that you need to look out for here. Each worker, to start, is going to try to reserve a CPU and then start a mini interpreter engine on that CPU. And then second, any data that all of those parallel processes need are typically going to be copied to each worker. I've tried both Python and MATLAB have objects that they advertise as being able to share data between parallel processes, and they work as far as the data is available to all of them, but for my test, they still copy the data. So if you have 1 gigabyte of data splitting it among 12 processes, you're going to end up with 12 gigabytes of data, 12 gigabytes in your RAM, which, depending on if you're on a laptop, that might be a problem. If you're on a server and you're not working with a gigabyte, you're working with more, then that might be a really big problem. If anyone has figured out that solution to something that either MATLAB or Python can do to not explicitly copy that data, I'd love to hear it. I haven't figured it out yet. I'm still working on it. And for large data, that data copying process is probably going to be the biggest processing overhead in your entire block of code. So that was mainly what I wanted to talk about. I guess questions at the end, and feel free to email me with questions about any of the notebook examples or anything like that.